March 10, 1945, Remagen, Germany. Lieutenant Colonel David E. Pergrin stands at the eastern bank of the Rhine River, his boots sinking into German soil, watching as the final steel treadway section locks into place. Behind him stretches 1,100 feet of floating bridge, pneumatic rubber pontoons supporting steel tracks, carrying an endless column of Sherman tanks and supply trucks into the heart of the Reich. 36 hours ago, this bridge did not exist. Pergrin's hand rests on one of the pneumatic floats, feeling it flex slightly as a tank rumbles overhead. Each float, 33 feet long, inflated with compressed air, supports thousands of pounds of American armor. The engineering is simultaneously crude and brilliant. Rubber balloons holding up the invasion of Germany. This cannot be how you conquer Europe, he thinks, building highways on water while the enemy shoots at you. But it is, and it works. The bridge behind him is already legendary. First Allied tactical bridge across the Rhine, longest pontoon bridge built under enemy fire in modern warfare. Constructed while German artillery pounded the construction site, while Luftwaffe fighters strafed the engineers, while the river itself fought against every connection point with a current running 6 knots downstream. The 291st Engineer Combat Battalion, supported by the 988th and 998th Treadway Bridge Companies, had accomplished what German Field Marshal Walter Model believed impossible. They had bridged the Rhine faster than the Wehrmacht could destroy it. 10 days earlier, the Ludendorff Bridge at Remagen, the last intact bridge across the Rhine, had fallen unexpectedly into American hands. For 7 days it held, allowing 6 divisions to cross. Then on March 17th, weakened by German bombs and the weight of American traffic, the bridge collapsed into the Rhine, killing 28 engineers and injuring 93 more. The race was on. The Americans needed bridges, immediately. Multiple bridges that could support tanks, artillery, supply convoys, bridges that could be built faster than the Germans could target them. Pergrin's bridge, completed at 17:10 hours today, proved it could be done. But this was just the beginning. All along the Rhine, from Remagen in the south to Wesel in the north, American and British engineer battalions were assembling pneumatic floats, connecting steel treadways, and transforming the river from Germany's final fortress into a highway system. The Germans had spent months destroying every permanent span across the Rhine. They believed the river, 980 feet wide at Remagen, flowing fast and cold, would buy them 6 weeks to regroup, to fortify, to prepare a final defense. They were wrong. The Allies didn't need the old bridges. They had brought their own bridges with them, packed in trucks, ready to assemble. The story of how they did it and why it mattered begins 4 years earlier in a military engineering laboratory where American engineers were designing the weapon that would crack open Germany's last line of defense. This was the innovation that changed everything. If you want to see how this discovery rewrote history, support us with a like. It helps us uncover more buried stories like this. Subscribe if you haven't already. Back to that moment of ingenuity in the laboratory. The journey to Remagen's floating highway began in 1940 when U.S. Army Corps of Engineers faced a fundamental problem. How do you move an armored division across a major river when the enemy has destroyed every bridge? Traditional military bridges, wooden pontoons, and fixed steel spans were too slow to construct, too vulnerable to artillery, and too limited in weight capacity. The new M4 Sherman tanks weighed 33 tons. Armored divisions needed bridges that could support 40-ton loads. Engineers needed bridge systems that ordinary soldiers could assemble without specialized training or heavy equipment. The answer emerged from the Army's Yuma Test Branch, the M2 Steel Treadway Bridge. The design was revolutionary in its modularity. Each bridge consisted of standardized, interchangeable components. Steel treadways, 12-foot sections of reinforced steel track, each weighing approximately 900 pounds, connected rigidly by 2 treadway pins at each joint. The treadways formed 2 parallel tracks, a continuous roadway capable of supporting medium tanks. Pneumatic floats, the innovation that changed everything. Each float measured 33 feet long and 8 feet 3 inches wide, constructed of rubberized fabric separated by bulkheads into 12 airtight compartments. When inflated with compressed air to 2 feet 9 inches deep, each pneumatic float could support 18 tons. Saddles, knockdown steel frames that sat atop the floats, distributing the weight of the treadways and vehicles across the pneumatic surface through 8 bearing plates. The system's brilliance lay in its transportability. A single pneumatic float, deflated and folded, could fit in the back of a 2.5-ton truck. 25 such trucks could transport enough equipment to build an 1,152-foot bridge, 93 pneumatic floats, the corresponding steel treadways, saddles, anchors, and connection hardware. One bridge set provided 864 feet of floating bridge. For larger rivers, multiple sets could be combined. The M2 could be built of floating spans, fixed spans, or a combination of both. Shore connections could be made by resting end treadways on abutment sills or using trestle spans. According to Army doctrine, trained engineer battalions could construct 362 feet of M2 treadway in 5.5 hours during daylight, 7.5 hours at night. Lieutenant Colonel David Peregrine, who would later command the 291st at Remagen, noted that in practice, experienced crews could sustain approximately 50 feet of construction per hour under ideal conditions, but the Rhine would not offer ideal conditions. The first combat deployment of the M2 treadway system came in the European theater in 1944, following the Normandy invasion. Engineer combat battalions built bridges across the Seine, the Meuse, the Moselle, each crossing teaching lessons about current management, anchor placement, and construction under fire. The Seine crossing demonstrated that pneumatic floats, despite their vulnerability, could withstand small arms fire without catastrophic failure. The 12 separate airtight compartments meant that even if several were punctured, the float retained enough buoyancy to function. The Moselle crossings proved that M2 bridges could be constructed under artillery fire. Engineer battalions learned to work through bombardment, to replace damaged sections on the fly, to keep construction moving even when casualties mounted. But nothing prepared them for the Rhine. The Rhine River, flowing 765 miles from the Swiss Alps to the North Sea, represented Germany's geographical last stand. At crossing points like Remagen, the river measured 980 feet wide. At Wesel, in the north, it exceeded 1,300 feet. The current ran 6 to 8 kilometers per hour, approximately 3.2 to 4.3 knots, powerful enough to tear improperly anchored bridges downstream or snap connecting cables under tension. The river's depth varied from 15 to 25 meters in main channels. Its banks, in some areas, rose steeply with rocky cliffs. The March water temperature hovered just above freezing. Any engineer who fell in had minutes before hypothermia became life-threatening. By March 1945, 22 road bridges and 25 railroad bridges had once spanned the Rhine. On March 1st, only 4 remained standing. By March 9th, after the Germans destroyed the bridge at Bonn, only the Ludendorff Bridge at Remagen survived, and it would collapse on March 17. The Germans had executed their demolition strategy perfectly. Field Marshal Walter Model's Army Group B had withdrawn across the Rhine, destroying every span behind them. German strategists believed the river would hold the Allies for weeks, perhaps months. The width, current, and lack of crossing points created what appeared to be an impenetrable barrier. They had not accounted for the floating highways packed in American trucks. They had not calculated the speed at which M2 treadway bridges could be assembled. They had not anticipated that American industrial capacity had transformed bridge building from specialized construction into mass production assembly. The mathematics were brutally simple. The Germans could destroy bridges faster than they could be built, but only if those bridges were permanent structures. If the bridges were temporary, modular, and could be assembled in hours rather than years, the equation reversed. The Allies could build bridges faster than the Germans could destroy them. That equation would determine the war's outcome. March 7, 1945, the pattern began at Remagen. When elements of the 9th Armored Division captured the damaged but standing Ludendorff Bridge, they achieved the impossible, an intact crossing over the Rhine. Within 24 hours, 6 battalions from the 5th Infantry Division reached the east bank. Within 48 hours, elements of 3 divisions, the 9th, 27th, and 78th, were across, establishing a bridgehead 6 divisions strong. But the bridge was dying. German bombs had damaged it during the capture. American traffic, thousands of vehicles, scores of tanks, stressed it beyond design limits. Engineers inspected the structure daily, noting cracks in the steel, movement in the foundations, weakening in the span. On March 17th at 3 p.m., the inevitable occurred. The Ludendorff Bridge collapsed into the Rhine, killing 28 American engineers and wounding 63 more who had been working on reinforcements. The bridgehead now had 125,000 troops on the wrong side of the Rhine with no bridge. The Army's response demonstrated the pattern that would define the campaign. Within hours, engineer units converged on Remagen with truckloads of bridge equipment. The 51st Engineer Combat Battalion arrived. The 291st Engineer Combat Battalion received orders to construct an M2 Treadway bridge. Heavy pontoon battalions moved up with aluminum alloy pontoons. Treadway companies brought their specialized equipment. The 291st began construction at 8:30 hours on March 9th. Lieutenant Colonel Pergrin supervised as his battalion, assisted by platoons from the 299th Engineer Combat Battalion and supported by the 988th and 998th Treadway Bridge Companies, assembled the floating highway section by section. The work was systematic but brutal. Pneumatic floats, inflated in rear areas, were trucked to the riverbank. Engineers manhandled them into position in the water, fighting the 6-knot current. Saddles were assembled atop each float. Steel treadways, 900 pounds each, were positioned across the saddles, then locked in place with connecting pins. Each 12-foot section extended the bridge toward the opposite bank. German resistance was savage. Artillery targeted the construction site continuously. Luftwaffe fighters strafed the bridge. German frogmen attempted to swim to the bridge with magnetic mines. On March 10th, one frogman was caught in the anti-mine boom upstream. Both disc-shaped mines he carried were set to detonate at 0600 hours the next morning. Despite all obstacles, Peregrine's engineers completed the bridge. At 1710 hours on March 10, 1945, just under 36 hours after starting construction, the eastern end of the 1,100-foot M2 Treadway Bridge touched German soil. The first Allied pontoon bridge across the Rhine was operational. The bridge carried traffic immediately. Sherman tanks, supply trucks, artillery tractors, jeeps, the American war machine rolled across rubber and steel into Germany's heartland. Signs at either end read, "The longest tactical bridge built first across the Rhine, constructed by 291st Engineer Combat Battalion and the 998th Treadway Bridge Company." But Remagen was merely the beginning. The pattern would repeat up and down the Rhine as March progressed. March 22-23, 1945, General George S. Patton's Third Army crossed at Oppenheim and Nierstein, south of Mainz. The 5th Infantry Division made assault crossings in the early morning hours of March 23rd. The 150th Engineer Combat Battalion, working in the rear area, inflated pneumatic floats and moved them to the river by truck. By daybreak, they had assembled the floats into rafts. By approximately 1800 hours that evening, a Class 40 M2 Treadway bridge was operational. Construction time, approximately 14 to 15 hours, though specific records vary by source. The following day, a second bridge, 1,280 feet, Class 24, was completed nearby. At Nierstein, the 249th Engineer Combat Battalion completed a 366-meter or 1,200-foot floating bridge in 18 hours. March 24, 1945, Operation Plunder, Montgomery's massive set-piece crossing near Wessel, included multiple bridge constructions. The 17th Armored Engineer Battalion, part of the U.S. 2nd Armored Division, built a 1,152-foot bridge using 93 pneumatic floats. Construction began at 0945 hours. By 1600 hours, 6 hours and 15 minutes later, the first truck crossed. 25 2.5-ton trucks had transported the bridge parts to the construction site. The pattern was clear. American engineers could build bridges faster than the Germans anticipated, under conditions the enemy thought impossible. The floating highways were turning Germany's last natural fortress into a highway system. The question was no longer if the Allies could cross the Rhine. The question was how many bridges they could build before the war ended. But understanding the full significance of the Rhine crossings requires examining what the bridges actually were and what made them work despite conditions that should have rendered them impossible. The M2 steel Treadway Bridge was, at its essence, an engineering paradox, heavy-duty military highway supported by inflatable rubber balloons. Each pneumatic float consisted of rubberized fabric, the same material used in life rafts and weather balloons, shaped into a long, rectangular tube. The outer perimeter formed the main inflation chamber. A removable center tube provided additional buoyancy. The floor distributed weight evenly across the bottom. Most critically, bulkheads divided the interior into 12 separate airtight compartments. This compartmentalization meant combat damage rarely proved catastrophic. German small arms fire could puncture 1 or 2 compartments, the float would sag slightly but remain functional. Even artillery fragments that tore multiple compartments left enough intact chambers to maintain partial buoyancy. Engineers could patch damaged sections while the bridge remained operational, or swap out damaged floats without stopping traffic. The current presented the greatest engineering challenge. The Rhine at Remagen flowed at approximately 6 knots. At Wessel, the current ran even faster in some channels. This seemingly modest flow rate translated to tremendous force when applied to a 1,000-foot bridge with nearly 100 floats creating drag. Engineers used multiple anchoring systems to hold bridges in position. 100-pound kedge anchors attached by 200 feet of 1-inch manila rope were positioned upstream at regular intervals. The anchors dug into the riverbed as the current pushed against the bridge, creating a dynamic equilibrium. When traffic crossed, the bridge would flex and move slightly. Engineers called it breathing, but the anchor system prevented catastrophic downstream drift. Shore connections required careful engineering. At Remagen, engineers rested the end treadways on abutment sills constructed on the riverbank. At other crossings, where banks were too steep or unstable, they used trestle spans, knockdown steel frameworks with adjustable heights to transition from shore to floating span. The construction process itself represented choreographed, controlled chaos. In rear assembly areas, engineers inflated pneumatic floats using portable air compressors. Each float required approximately 30 minutes to inflate to its full 2 feet 9 inches depth. Compressors ran continuously, working through sets of floats while trucks waited to transport the completed assemblies forward. At the riverbank, engineers divided into specialized teams. Float handlers maneuvered the inflated pontoons into the water, fighting current and wind. Saddle crews assembled the knockdown steel frames atop each float, securing them with rope girdles. Treadway teams lifted the 900-pound steel sections, usually 6 to 8 men per treadway, and positioned them across the saddles. Connection crews drove treadway pins through aligned holes, locking sections rigidly together. Anchor crews deployed kedge anchors upstream, paying out rope to calculated distances. The work proceeded under fire. At Remagen, German artillery shells impacted near the construction site throughout the 36-hour build. Casualties mounted. 35 engineers were wounded during construction. Debris floating downstream, trees, destroyed equipment, occasionally bodies, threatened to crash into the partially completed bridge, potentially breaking connections or tearing floats. At Nierstein, German artillery fire at dawn on March 23 interrupted construction. American troops on the east bank silenced the guns, allowing work to resume. Luftwaffe bombing and strafing attacks continued through the morning, wounding one engineer but causing minimal structural damage. The bridges, once completed, operated under constant threat. German frogmen, divers equipped with magnetic mines, attempted to approach bridges underwater. Americans installed anti-mine floating log booms upstream, followed by anti-personnel booms made of Admiralty netting. At Remagen, frogmen were caught twice in these nets, both times carrying disc-shaped magnetic mines set for timed detonation. Bridge guards maintained 24-hour surveillance. Traffic control officers managed the endless flow of vehicles, tanks, trucks, jeeps, artillery tractors, ambulances. Doctrine specified that bridges should operate under blackout delineation at night, with minimal lighting to guide vehicles while denying German artillery accurate targeting information. Maintenance never stopped. Engineers inspected every saddle connection, every treadway pin, every anchor line. The river's constant pressure combined with vehicle traffic created continuous stress. Ropes stretched, pins loosened, floats developed slow leaks. Maintenance crews worked around the clock, making repairs while traffic continued. The capacity of M2 treadway bridges astonished even the engineers who built them. A Class 40 bridge could support vehicles up to 40 tons, including fully loaded M4 Sherman tanks, 33 tons, and M26 Pershing tanks, 41.7 tons, passing slowly. Traffic capacity under optimal conditions exceeded 1,000 vehicles per day on a single bridge. At Remagen, Pergrin's Bridge carried the entire 78th Infantry Division across in less than 24 hours. At Oppenheim, by March 25th, more than 15,000 troops had crossed via landing craft, followed by tanks and artillery crossing on completed bridges. Within 2 weeks of the first Rhine crossing, more than 60,000 military vehicles had crossed the river in Third Army's sector alone. The technical achievement becomes clear when compared to traditional military bridging. Bailey bridges, the British modular truss system, offered superior load capacity and durability, but required significantly longer construction time and more specialized equipment. Fixed bridges required prepared abutments and foundations. Both types needed time the Allies did not have. The M2 treadway system succeeded because it optimized for speed of construction under fire. Each component was standardized, allowing any trained engineer to work on any section. Components were light enough for manual handling, no cranes required, but strong enough to support armor. The modular design meant damaged sections could be replaced without rebuilding the entire span. Most critically, the pneumatic floats transformed bridge construction from civil engineering into industrial production. Manufacturing rubber floats in quantity proved easier than manufacturing steel pontoons or fabricating truss sections. Deflated floats occupied minimal transport space. A single division's engineer battalions, properly equipped and supplied, could construct multiple bridges simultaneously. The Germans had bet that destroying permanent bridges would stop the Allied advance. They calculated correctly that reconstructing stone and steel spans would take months. They did not anticipate that the Americans would sidestep the problem entirely by building temporary bridges at industrial scale. The Rhine crossings proved that 20th century warfare had changed. Industrial capacity no longer simply supplied armies, it transformed the battlefield itself. American engineers were not rebuilding destroyed infrastructure. They were manufacturing new infrastructure on site, faster than the enemy could destroy it. The equation Field Marshal model relied upon, destruction faster than construction, had been reversed. The Allies were building bridges faster than the Germans could target them. The Rhine, rather than stopping the invasion, had become a construction site, and the American war machine was pouring across rubber and steel into the collapsing Reich. The story of the M2 treadway bridge's development reveals why American military engineering succeeded where German strategy failed. Fundamentally different philosophies about how to win modern war. The requirement for a new tactical bridge system emerged in 1940 as American military planners studied the German blitzkrieg in Poland and France. Traditional pontoon bridges, wooden boats supporting wooden decks, could not support the new generation of medium tanks. The Army needed bridges that combined three seemingly incompatible qualities: heavy load capacity, rapid construction, and easy transportability. The design team faced the mathematics of an impossible problem: a bridge capable of supporting 40-ton tanks required substantial buoyancy. Traditional solutions, steel pontoons or aluminum alloy half pontoons, provided the necessary buoyancy but created transport nightmares. Steel pontoons were heavy and bulky. Aluminum pontoons, while lighter, still required significant truck space. A single bridge set using aluminum pontoons required dozens of trucks for transport. The breakthrough came from the pneumatic float concept. An inflatable pontoon, when deflated, occupied a fraction of the space of a rigid pontoon. 25 2.5-ton trucks could transport a complete bridge set, enough for 864 feet of bridging. The same bridge, using rigid pontoons, would require perhaps 3 times as many vehicles. But inflatable pontoons introduced new vulnerabilities. Rubber fabric could be punctured by small arms fire. A catastrophic deflation could collapse an entire section. The engineers solved this by dividing each float into 12 separate compartments. Damage to 1 or 2 compartments reduced but did not eliminate buoyancy. The float would ride lower in the water but remain functional. The steel treadway design reflected similar thinking. Rather than a continuous roadway, the bridge used 2 parallel tracks, like railroad rails made wide enough for tank treads. Vehicles drove with tracks or wheels on the steel treadways, leaving the center section open. This reduced the amount of steel required, cutting weight and cost without compromising strength. The modular connection system was the final piece. Treadway sections locked together with simple pins, 2 per joint, driven through aligned holes. No welding, no bolting, no specialized tools. Any soldier with a sledgehammer could connect sections. Damage to one section meant replacing that section, not rebuilding the entire bridge. The Army tested the M2 system extensively at the Yuma Test Branch before the Normandy invasion. Engineers learned that successful deployment required training in specific assembly sequences, anchor placement calculations for different currents, and rapid response to combat damage. But the fundamental design proved sound. Pneumatic floats worked. Production began in 1943. Manufacturing priorities went to rubber companies already producing life rafts and aircraft components. By 1944, thousands of pneumatic floats, steel treadways, and associated equipment were being shipped to Europe. Engineer combat battalions and specialized treadway bridge companies received training on the system. The American design philosophy emphasized 3 principles. Speed over permanence. The M2 was explicitly designed as a temporary structure. It would last weeks or months, not years. This allowed lighter construction, simpler materials, faster assembly. Modularity over customization. Every component was standardized. Engineers didn't measure and cut for specific sites. They assembled pre-manufactured sections. If a site required 1,000 feet of bridging, they used the number of sections that equaled 1,000 feet. Mass production over craftsmanship. The system could be manufactured in quantity with existing industrial capacity. It didn't require specialized steel mills or precision engineering facilities. Compare this to German military bridging in 1945. The Wehrmacht used primarily captured equipment or improvised ferries. German bridge trains had been largely destroyed or abandoned during the retreat across France. German industry, under constant bombardment and resource shortages, struggled to produce basic supplies. Manufacturing specialty bridging equipment ranked low on priority lists, dominated by ammunition, fuel, and replacement weapons. The philosophical difference went deeper than engineering. The American approach assumed abundance. Abundant manufacturing capacity, abundant transport, abundant trained personnel. The M2 system was designed for an army that could afford to transport thousands of pneumatic floats, to deploy entire battalions for single bridges, to build multiple bridges where one would theoretically suffice. The German approach assumed scarcity. Scarce resources, scarce transport, scarce time. German strategy in March 1945 relied on making the enemy pay maximum cost for minimum gain, destroy the bridges, force the Allies to rebuild under fire, make every mile cost lives and time. But this strategy failed against an enemy who didn't need to rebuild bridges. The Americans simply constructed new ones, faster than German artillery could target them effectively. The design philosophy extended to operational doctrine. U.S. Army Engineer School doctrine specified that bridge construction should proceed continuously regardless of enemy fire. Casualties would be replaced, damaged equipment would be swapped out, construction would not stop. This doctrine only worked for an army with deep reserves of personnel and equipment, precisely what the U.S. Army possessed in March 1945. The M2 Treadway Bridge represented the American way of war in microcosm: overwhelming material superiority, industrial-scale logistics, standardized systems deployed by adequately trained personnel rather than specialized craftsmen. It was war as mass production. The Germans, fighting the American way of war, faced an enemy who could build bridges faster than the enemy could destroy them. They faced an enemy who could accept bridge casualties, 35 wounded at Remagen, and continue construction without pause. They faced an enemy who didn't need Germany's bridges because that enemy had brought his own bridges with him. The strategic irony was complete. Germany had spent months preparing the Rhine as their last defensive line. They had demolished their own infrastructure to create that defense, and then they discovered that destroying bridges only worked against enemies who needed those specific bridges. The Americans didn't need the bridges at Cologne, Bonn, or Mainz. They only needed the river to be wide enough to justify using their floating highways. The mathematics were brutally simple. American industrial capacity had transformed military engineering from problem-solving into manufacturing. The Rhine wasn't a barrier, it was a production site, and American engineers were mass-producing solutions faster than German forces could respond. The consequences of the floating highways played out across 3 weeks in March 1945 as the Rhine transformed from Germany's last fortress into the Allies' supply route. March 7th to 17th, the Remagen bridgehead. For 10 days, the damaged Ludendorff Bridge held. In that time, elements of 6 divisions crossed into Germany. The 310th Infantry Regiment of the 78th Division was among the first to cross, fighting their way into Erpel, then north along the riverbank to Honnef. The 9th Armored Division expanded the bridgehead. The 78th Infantry Division fought through to Buell on the east bank, establishing positions that would anchor further operations. German resistance was fierce but increasingly desperate. Field Marshal Model, commanding Army Group B, threw everything available at the bridgehead. Panzer units fired direct artillery at bridge construction sites from positions in Erpel. Luftwaffe aircraft made repeated bombing and strafing runs. German frogmen equipped with magnetic mines attempted underwater approaches. All failed to dislodge the Americans or destroy the bridges. When the Ludendorff Bridge collapsed on March 17th, it mattered less than the Germans hoped. By then, Lieutenant Colonel Pergrin's M2 Treadway Bridge was operational. Additional pontoon bridges were under construction. The 51st Engineer Combat Battalion had built bridges. Assault boats and landing craft ferried troops continuously. The Rhine at Remagen had become not a single crossing point, but a logistics zone with multiple bridges and ferry operations. Statistics tell the story. By March 25th, more than 125,000 troops occupied the Remagen bridgehead. Ammunition dumps on the east bank supported artillery batteries shelling deeper into Germany. Supply convoys ran 24 hours daily. The bridgehead expanded to 25 miles wide and 10 miles deep. March 22nd-24th, Patton's Crossing. Third Army's Rhine crossing at Oppenheim and Nierstein demonstrated the speed advantage of the M2 system. The assault began at 2200 hours on March 22nd with infantry crossing in assault boats. By dawn on March 23rd, 6 battalions from the 5th Infantry Division held the east bank. Engineer battalions moved up immediately. The 150th Engineer Combat Battalion began inflating pneumatic floats in rear areas at 30:30 hours. By daybreak, rafts were assembled. By approximately 1800 hours, the first Treadway Bridge was operational, approximately 14-15 hours from start to completion. The speed stunned German defenders. Traditional military thinking held that major river crossings required days of preparation, artillery bombardment, and coordinated assault. Patton's forces crossed with minimal artillery preparation, partly to maintain tactical surprise, partly because they didn't need it. The engineers could build bridges faster than German artillery could target them effectively. Within 48 hours of the initial assault, 4 American divisions were across the Rhine in Third Army sector. By March 25, more than 60,000 vehicles had crossed. The 4th Armored Division, exploiting bridges built by engineer battalions, completed their 1,152-foot bridge in 6 hours 15 minutes. British, American, and Canadian engineers built 27 temporary bridges in the sector from Dinslaken to Emmerich. The coordinated construction created a transportation network rather than isolated crossing points. Within 72 hours of the initial assault, the Rhine in the Wesel area was crossed by enough bridges to support Army Group operations. Traffic moved continuously. The bridgehead expanded rapidly against weakening German resistance. The human cost of bridge construction, while significant, remained sustainable given Allied reserves. At Remagen, 35 engineers were wounded during construction of Peregrine's Bridge. The Ludendorff collapse killed 28 and wounded 93. Additional casualties occurred at other crossing points from artillery fire, air attack, and construction accidents. But casualty rates were lower than anticipated. The speed of bridge construction, completing spans in hours rather than days, reduced exposure time. The mobility of pontoon bridges made them harder to target than fixed spans. The compartmentalized float design meant artillery hits rarely caused catastrophic structural failure. German attempts to destroy the floating highways proved increasingly futile. Artillery could damage sections but not collapse entire bridges. Air attacks faced dense anti-aircraft fire and rarely scored decisive hits. Frogmen were defeated by anti-miner booms and constant vigilance. The bridges, once completed, proved surprisingly robust. By March 31, 1945, less than 4 weeks after the first Rhine crossing at Remagen, all 4 American armies had crossed the river. First Army exploited the Remagen bridgehead. Third Army drove across at Oppenheim, Nierstein, Boppert, and St. Goar. Seventh Army crossed at multiple points in the south. Ninth Army participated in Operation Plunder at Wesel. The Rhine, Germany's final natural barrier and last major defensive line, had been thoroughly breached. German forces west of the Rhine were destroyed or captured. German forces east of the Rhine faced overwhelming Allied superiority in men, tanks, artillery, and air power, all being supplied continuously across the floating highways. Field Marshal Model's Army Group B, trapped in the Ruhr pocket as American forces swept beyond the Rhine crossings, faced inevitable collapse. Model refused to formally surrender but disbanded his army group, releasing youngest and oldest soldiers from service and allowing the rest to choose surrender or attempting breakout. Approximately 325,000 German soldiers surrendered. Model himself committed suicide on April 21, unwilling to witness Germany's final defeat. The floating highways had not just crossed a river, they had broken the back of German resistance in the west. Within 6 weeks of the first Rhine crossing, Germany would surrender unconditionally. The pneumatic float bridges, crude assemblies of rubber and steel built under fire by combat engineers, had achieved what months of bombing and years of ground combat had struggled to accomplish. They had opened the road into Germany's heartland, and the American war machine had poured through. The final numbers tell the story of industrial warfare at its most efficient and devastating. Bridge production statistics. M2 Treadway bridges built across the Rhine. Dozens of bridges at multiple crossing points, though exact comprehensive totals vary by source. Construction times, ranging from 6 hours 15 minutes, 1,152 feet at Wesel, to 36 hours 1,100 feet at Remagen under intense fire. Bridge capacity. Class 40 bridges supporting vehicles up to 40 tons. Traffic capacity. Individual bridges carrying 1,000+ vehicles per day. Engineer Battalion performance. The 291st Engineer Combat Battalion alone, during its tour in Europe, constructed 23 timber bridges, 44 Bailey bridges, 7 Treadway bridges, 11 bridges built under fire, 7 river assault crossings conducted. The battalion destroyed 6 bridges, German infrastructure, deactivated 15 bombs, cleared 7,000 mines, and took 8,500 German prisoners. From an initial force of approximately 600 men, the battalion suffered 93 wounded and 8 killed in action by war's end. Strategic impact. Within 2 weeks of the first Rhine crossing, more than 60,000 military vehicles crossed in 3rd Army sector alone. All 4 U.S. armies, 1st, 3rd, 7th, and 9th, had established bridgeheads. The Ruhr industrial heartland was encircled. German Army Group B, with 400,000 men, was trapped in the Ruhr pocket. Comparative analysis, American versus German approach. American engineering philosophy. Modular, mass-produced bridge components. Inflatable pneumatic floats, 33 feet long, 18-ton capacity, 12 compartments for redundancy. Steel treadways, 12-foot sections, 900 pounds each, pin-connected. Complete bridge sets, transportable by 25 trucks, 2.5 tons standard. Assembly feasible by trained combat engineers without specialized equipment. Construction doctrine, continuous assembly regardless of enemy fire. Industrial support, thousands of pneumatic floats manufactured and shipped to Europe. German defense philosophy, systematic demolition of permanent infrastructure, reliance on natural barriers to delay Allied advance, limited capacity to produce replacement bridging equipment, assumption that destroyed bridges would require weeks or months to replace. Strategy, make enemy pay maximum cost for minimum gain through defense in depth. The philosophical difference proved decisive. German strategy assumed the Allies needed Germany's bridges. American engineering demonstrated they only needed the river to be wide enough to justify using their own bridges. Final irony? The Germans destroyed approximately 40 bridges across the Rhine to stop the Allied advance. The Allies responded by building dozens more bridges in less than 3 weeks. The final result? More crossing points in March 1945 than had existed in February 1945, before the Germans began their demolition campaign. The Reich had demolished its own infrastructure to create a barrier. The barrier lasted less than a month against an enemy who manufactured infrastructure as a routine military operation. Return to March 10, 1945. Lieutenant Colonel Pergrin stands at the eastern bank of the Rhine as the last vehicles of the day cross his bridge. Behind him, the river continues its ancient flow toward the North Sea. Above him, the bridge flexes slightly with each passing tank, breathing, as his engineers call it, rubber and steel bending but holding. The examination at Remagen revealed more than engineering triumph. The pneumatic floats supporting tons of American armor represented a fundamental truth about modern warfare. Industrial capacity doesn't just supply armies, it transforms the battlefield itself. The floating highways across the Rhine accomplished what 4 years of combat had struggled to achieve. They eliminated the last significant barrier between Allied armies and the German heartland. Within 6 weeks of Pergrin's bridge touching the eastern bank, the war in Europe would end. The bridges themselves embodied an irony the Germans failed to anticipate. By destroying their permanent spans, the Wehrmacht forced the Allies to use temporary bridges, which turned out to be faster to build, harder to destroy, and more flexible to deploy than the original permanent structures. German strategy assumed destruction was their strongest weapon. It proved to be their fatal miscalculation. The M2 Treadway bridges were not sophisticated. They were crude assemblies of inflatable rubber and steel plates. They bounced under traffic. They required constant maintenance. They would last months, not years, but they could be built in hours under enemy fire by ordinary combat engineers using equipment transported in standard trucks. That combination proved unbeatable. The broader lesson transcended military engineering. The Rhine crossings demonstrated what happens when industrial-scale production meets tactical deployment. American engineers weren't solving unique problems with custom solutions. They were manufacturing standard solutions and deploying them at volume. They were treating bridge construction like an assembly line, standardized components, trained workers, high-speed production. Germany, fighting the American way of war, faced an enemy who could accept casualties, replace losses, and continue operations without pause. An enemy who didn't need to be brilliant, just adequately competent at industrial scale. An enemy who had transformed military engineering from specialized craft into mass production. The examination of Remagen's bridge provided the final proof. The structure was not poorly designed, it was brilliantly designed to achieve specific goals: rapid construction, heavy load capacity, easy transport, simple assembly. Those goals simply did not include permanence, elegance, or traditional engineering aesthetics. And in that single fact lies the entire story of why Germany lost the war. The American war machine didn't need Germany's bridges. It brought its own bridges, packed in trucks, ready to assemble. The Rhine wasn't a barrier, it was a construction site. And American engineers built highways faster than the Wehrmacht could destroy them. Peregrine's Bridge at Remagen still stands in historical memory as the first Allied tactical bridge across the Rhine, but its real significance lies in what it represented, the moment when American industrial capacity proved unstoppable not through sophisticated technology, but through crude, fast, mass-produced solutions deployed at overwhelming scale. Germany destroyed its bridges, America built highways. The outcome was never in doubt once that equation became clear.